Hello, mechanical vibrations are described with differential equations. And as you may expect, this is a natural place for differential equations to earn their living, as one of the very basic things is to describe displacement or motion, and therefore the equations of motion are keeping track of rates of change of first order and second order and so on. Well, let's consider this system. As you can see in this animation, there is a mass here denoted as a square attached to a spring that is hanging. This is very commonly referred to as a spring mass system, and what we're seeing in this animation is basically how this is vertically, it kind of goes down and up and down and up. So let's take a closer look at a snapshot of this motion. So let's first say that, use some notation here. Let's say that the mass is denoted with the letter M here. And as we saw previously, there was some kind of force that was kind of pulling this mass down. And so that force can be denoted as F as a function of time. And then somehow well, another constant here that will play a role is the constant K, that will be directly related to the spring here. And there is something that is going to be considered in this system that's called damping. Okay, and then that action of the damping is going to be denoted with the letter C. So f of t is going to be considered a force, an external force, and K is going to be called the constant related to spring, or spring constant. So we're going to think of t as an independent variable, and x of t, this x of t is going to denote, well, distance. In some other applications of this type, you'd say distance traveled, but it really is displacement of the mass. So we could think of this very same picture as basically what would happen if we grab this picture and we look at this horizontally instead of vertically. In other words, what happens if we rotate this picture left? We're going to have very much the same thing, but with a different orientation. And this is a schematic of the spring mass system if we now are looking at this horizontally instead of vertically, right? And maybe we can describe a few things. So we're going to assume here that the mass of the spring here denoted by M is a positive real number, and this constant K, we're going to assume that K is also a positive real number, and the other parameter we call C is either 0 or positive. So M, K, and C are real numbers with these constraints. So X, as we were saying, X is a function of time t, and when X is 0, we're going to consider this the so-called rest position at rest. And since we're looking at this horizontally, we're going to keep track of the displacement of the mass growing to the right. Okay, so as the mass is going away from, this is the wall, then we're going to consider that displacement as a function of time. The second law of Newton tells us that the force is equal to the mass times acceleration. Okay, so the mass times acceleration is going to be equal to the force, which in this case will be translated as f of t minus c times x prime minus kx. The term kx has to do with the fact that the force exerted by the spring is proportional to the compression of the spring in virtue of a law called Hooke's law. And there is a sense of negative direction when, well, this is standard derivation or application of Hooke's law. And also the other term here involves the first derivative of displacement, and that is modeling the force exerted by friction, and that force that is exerted by friction is proportional to the velocity of the mass. So you can see how this constant, this parameter, constant parameter c, is acting here as a means of proportionality in the sense of friction. So we can rewrite, this is a differential equation in x, and we can rewrite this as mx double prime plus c x prime plus k x equals to f. And we see here this coefficient m, coefficient c, and coefficient k, they're all constants, right? So this is an equation that is linear in terms of derivatives up to order 2, and it has constant coefficients. So we're going to consider this equation now, and a couple of scenarios here. If that force on the right side of this second order differential equation with constant coefficients, if we consider that right side, which we're calling external force, if that is a constant function which is equal to 0, identically 0, then the system would be considered unforced or free. On the other hand, if that external force is a function that is not identically equal to 0, the system is then dubbed forced. On the other hand, if this coefficient c, this parameter c, is equal to 0, that means that the second order equation has only the second derivative and the function. There is no first derivative. If c equals to 0, then the system would be considered undamped, okay? And if this constant is strictly positive, if c is strictly positive, then we would consider the system damp, a system that is suffering the effect of damping. So whenever that constant c is strictly positive, then the system is damp. Whenever that c is 0, the system is not experiencing any effect on damping. So let's now consider another scenario in which we have a so-called pendulum, right? So this type of system will be related to the mass spring system. And so here we have an animation of this sphere basically bouncing there. You may just think of that darker line that's connected to that sphere. That sphere is also kind of has two additional, one V and one A. You can ignore those things for now, but we're simply interested on this darker line connecting the sphere to, maybe that's the wall or some center of operation or something like that. And you can see how this theta is an angle that appears to form there between the dash line and that line that's sustaining the sphere. So this system is called a pendulum, and then there is an angle that's being formed there with this dash axis. So a snapshot of this scenario in which the mass of the pendulum is m and that pendulum has length L, okay? So here what we're interested in is this angle theta, and we're going to think of theta as a function of time. So as time being the independent variable, as time progresses, that angle is a function of time. Okay, so we can involve here constant g, which denotes the force of gravity. So G denotes a force of gravity, and we can then derive the equation theta double prime plus G over L times sine of theta equal to 0. So in this case, if you want to know where this comes from, so maybe we can make an argument. And what we know is the acceleration is the length times the second derivative of theta, and the mass of the pendulum is m. So the acceleration times the mass is equal to the tangential component of the force given by gravity, and that is precisely given by the term mass times gravity times sine of theta. Okay, so this equation here is an application of Newton's second law, and you can see how canceling the mass m, then that equation can be written as the previous equation we had. Almost, right? There is one thing that I'm missing here for those two equations to be the same, and is that I neglected there is a negative sign here on the left hand side. So it's negative mg times sine of theta, because because mg sine of theta is considered in the opposite direction. So we're going to do an approximation. I want to refresh your mind as to what the function sine of theta looks like. So here, this is a sketch of sine of theta. Okay, this think of this function. This is 0 here, and we could sketch the function on the other side. But the idea is that this function is not linear. Okay, this function is not linear, but it's not linear as a whole. But we're going to consider an approximation around 0, specifically very, very close to 0 here. So what happens if in an interval around 0, we consider an approximation of sine with a line? So you can see that I'm trying to position a line there, and basically by doing that, I want to make the approximation that sine of theta is equal to theta. This is only valid on a neighborhood of 0. Okay, and that is precisely the idea with this graph here. This is this curve here denotes sine of theta, and this is a line that is theta. So there is a section around 0 at which the line and the sine function are basically very close to each other. So when theta is small, or is close to 0 from the left or right, we could approximate sine of theta with theta, and then the equation of motion becomes this equation. And so basically what this is telling us is that when the swings in the pendulum are small, then we can model the behavior of the system with a simpler linear equation. This, if I remind you, the original equation is this, which comes from a derivation or an application of Newton's second law. The second law, this involves a derivative of order 2, but this equation is not linear in theta. But by making an approximation for theta relatively small, this now becomes a second order linear ordinary differential equation with constant coefficients, right? So here is 1, and G over L is also a constant.